exactly in the same way, we can slew the spheres to do a combined correction for delta and eco. Now, इस पे बेटा हमारे एग्जाम में numerical आता है. So today the first thing which we are going to see is that numerical, how to tackle that kind of a numerical, what do they ask? And फिर इसके बाद जो next चीज़ें हमारे plan में आएंगी, those are number one, the healing error. What is the cause? What is the correction? And after that we have the compass correction, the total procedure, full procedure of compass correction. How do you correct a compass of a brand new vessel? So after these two, I'm going to show you some typical questions which come in our papers based on the concepts of magnetism. So that's the plan for today. Some candidates have requested me to finish the class little earlier, say by about 7:30 or so. Let's see if we can cover up the topics.
Yes, sir. Yes, sir. Thank you, sir.
Okay. Okay. So the time is around 8 o'clock. Okay. Anyway, we'll try to finish.
7:47 time, sir. Similar.
Okay. All right. So we'll try to finish by about 7:30. Let's see. ओके दूसरी चीज़ बेटा, आज थोड़े कॉम्प्लिकेटेड क्वेश्चन आने वाले हैं. सो बी केयरफुल, ग्रैब ए कप ऑफ टी और कॉफ़ी, रिमेन फ्रेश एंड पे अटेंशन टू मी, राइट? ओके, ऑल राइट बेटा, लेट्स स्टार्ट ऑफ. Let me first take you to the numerical question, which is based on the combined delta and eco correction. Let's go. All right. So let's go, beta. I am putting up the presentation now. We will see this numerical question first. Let's go. Now let's try to understand the combined correction of coefficient delta and eco, this concept, using a actual question. On a ship, the soft iron spheres are observed to be placed in a relative direction 100 and 280 with respect to the ship's head. Analyze the cause for same and find the heading on which the sphere correction should be done. This is the actual question which has come in the past papers on this particular topic. So let's first try to understand what the scenario is. What does the question mean? Let me show you a diagram. So we see the ship here, and on the ship we have the compass. The circle which you see in the center represents the compass, and the spheres are fitted on this ship in a relative direction of 100 and 280. This is a relative direction with respect to the ship's head. Let's assume for the time being that the ship is heading north. So this is the north direction as well as the ship's head, and the spheres are lying in a direction 100. So from the ship's head going clockwise up to an angle of 100, this is where one of the sphere lies. And going further, 100, 120, 130, 180, then 270 and 280. This is the direction in which the second sphere lies. So we are now able to see what is the orientation or location of the spheres with respect to the compass. So the first thing they are asking in the question is, analyze the cause for same. Now one thing which becomes clear to us is that on a normal merchant vessel, the spheres are usually placed in the athwartship direction. That means in a relative 090-270 direction. Now that happens when the ship only has coefficient delta. If coefficient eco is present, the spheres will be placed either northwest southeast or northeast southwest of the compass. We are aware that when both the coefficients are present, that is delta and eco, that is the case when the spheres are slewed at a particular angle, and that is the situation here. So this clearly tells us that on this particular vessel, we have coefficient delta as well as coefficient eco. Both these coefficients are present on the ship. And that is the reason why the spheres are slewed. They are fitted at an angle, not in the athwartship direction, but at an angle. Another thing which we observe is, looking from top, the spheres are slewed in a clockwise direction. If you see, they are slewed by an angle of 10 degrees in a clockwise direction. Looking from top, the spheres are turned in a clockwise direction. So this gives us the second inference here, that coefficient delta and coefficient eco are of the same sign. Because we are aware, when delta and eco are of the same sign, the spheres are slewed clockwise. If delta and eco are of the opposite signs, the spheres are slewed anti-clockwise. So that is the second inference which we get. First inference, this ship has coefficient delta as well as eco. Second inference, coefficient delta and coefficient eco are having the same sign. Now going further, we need to find the heading on which the sphere correction should be done on this particular ship. Now always remember the fundamental, that whenever we are doing any sphere correction, it may be coefficient delta, it may be coefficient eco, or it may be the combined correction for delta and eco. In all these cases, whenever we are doing any sphere correction, we have to ensure that the spheres are at a intercardinal direction from the compass location. That means the sphere should be either northeast of the compass, or southeast of the compass, or southwest of the compass, or northwest of the compass. Whenever the correction is being done, the heading of the ship should be such that the spheres are at a direction which is an intercardinal direction from the compass location. So for doing the combined correction also, we need to take the spheres to a intercardinal direction. Now let's assume we are trying to take the starboard corrector sphere to the southeasterly direction of the compass. Now if you want to take the starboard corrector sphere southeast of the compass, that basically means that the sphere has to be turned clockwise. The sphere has to be turned or slewed clockwise by an angle of 35 degrees. It is right now at an direction of 100, and we need to take it to a direction of southeast, which is 135. So we have to turn it clockwise by an angle of 35 degrees. Now that means the vessel has to swing to the starboard side. Turning clockwise, looking from top, means swinging to starboard. The vessel has to swing to the starboard side by an angle of 35 degrees. Now, if the ship swings to starboard by an angle of 35 degrees, the heading on which the ship would be that time is 035 degrees. So the heading of the ship will be 035 degrees. When the ship is heading 035, the starboard corrector sphere is going to come exactly southeast of the compass. Beta, up to here is clear. Any doubts coming in? Very good, beta. Great. The port side corrector will obviously automatically go to the northwest direction. The spheres are in reciprocally opposite direction. So if the starboard sphere comes southeast of the compass, the port corrector sphere comes northwest of the compass. So this is the heading on which the correction can be done. Now there is one more possibility which is available to us, and that possibility is, Instead of taking the starboard corrector sphere to southeast direction, we can also take the starboard corrector sphere to the northeast direction. That is also a intercardinal direction. So the starboard corrector sphere can be taken to the northeast direction also. Now for doing that, the sphere has to be turned anti-clockwise by an angle of 55 degrees. Northeast direction represents 045. The sphere is at a direction of 100. So it has to be turned anti-clockwise by an angle of 55 degrees. This basically means that the ship needs to swing to port. Let me show you with an arrow. You can see this red color arrow showing that the ship needs to swing in the port direction by an angle of 55 degrees. And if the ship swings to the port side by 55 degrees, the heading of the ship will be 305 degrees. So if the vessel heads 305, the starboard corrector sphere will come northeast of the compass and the correction can be done. The port corrector obviously will come in the southwesterly direction then. So both the spheres will be lying in the northeast southwest direction of the compass. So we have obtained two options. One is heading 035, the second one is heading 305. Now if you look carefully, even if the ship goes on a heading which is reciprocal of 035, reciprocal of 035 would be 215. Even on that heading, the spheres will be lying at an intercardinal direction. You see, at 035 heading, the starboard sphere was southeast of the compass. When the ship goes to 215 heading, reciprocally opposite heading, this starboard sphere will go to northwest of the compass, reciprocally opposite direction. So the correction is also possible when the ship is heading 215, and the same applies to 305 heading also. If the ship goes on a heading reciprocal of 305, which comes out to be 125 degrees, even on this heading, the correction can be done. So these are the four headings which we have obtained: 035, 125, 215 and 305. All these headings are perpendicular to each other at a 90-degree difference from each other, and the correction for combined correction for coefficient D and E can be made on any one of these headings. So the answer is obtained as heading has to be 035, 125, 215 and 305. Any one of these headings, the correction can be made. And the answer is thus obtained.
In exam, we can put directly answer with this diagram, or we have to write anything.
बेटा, along with this, जो मैंने अभी explain किया है, just put it in your own words in a point-wise form or a paragraph form. That would be enough.
Okay, sir.
Any more doubts, beta, in this?
Sir, in these type of questions, the spheres are always opposite. I mean, diametrically.
Yeah, that's correct, beta. Whatever is the case, whether it is delta correction or eco correction or delta and eco combined correction, you will see that the spheres are fit in a reciprocally opposite direction. They will be 180 degrees away from each other. So the angle would never be anything else. They will be reciprocally opposite directions.
And sir, any significance on the soft iron spheres part?
Significance, by significance, you mean, beta? What do you mean?
I mean, is the question, I mean, relating to only D and E correction by saying soft iron spheres?
Beta, the spheres, they do only delta and eco correction. Alpha correction is not usually done, Bravo correction is done by fore and aft magnets and flinder bar. Charlie correction is done by athwartship magnets and turning the flinders bar. Delta and echo are the two corrections which are related, the corrector for which is the sphere corrector. So whenever the question tells us about soft iron sphere, we know it has to be either delta or echo or a combination of both.
Okay, sir.
Sir, whether this port soft iron sphere distance and starboard side will be the same, or it will be depending on how we are correcting?
Okay, you mean to say the scale position of the spheres?
Yes, sir. There will be graduation, right, in the port sphere.
Yeah,
how much
that is correct. That is correct, बेटा. मैं आपको दिखा भी देता हूँ. Just give me a minute, I'll show you. ये देखो बेटा, ये आप अगर ध्यान से देखो तो जो ये पोर्ट बीम वाला जो स्फीयर है, रेड कलर का जो स्फीयर है, इसके नीचे आपको एक यहाँ पे ब्लैंक पोर्शन दिखाई दे रहा है. दिस इज ए स्लाइडर चैनल बेसिकली, एंड इसके ऊपर एक स्केल लगा होता है. इसमें 1 2 3 4 5 ऐसे मेंशन्ड होते हैं. The spheres can be brought closer to the compass or they can be pushed far away from the compass. Now that is what do we mean by scale position of the sphere. अगर आप अपना कंपस का डेविएशन कार्ड देखोगे which has been corrected by a compass adjuster, तो उसमें उसने clearly mention किया होगा the scale position of the spheres is 1.5 or 2 or 2.5 and so on. So usually this scale position should be the same for the port and starboard spheres. If one of them is at 2.5, the other also has to be at 2.5. This is for a normal merchant vessel. But in case you are on a special type of a ship, like a aircraft carrier where the compass is placed off the center line, yes, there it is possible that one of the spheres may be closer and the another one may be farther. Right, beta? Clear?
Clear, sir, clear.
वेरी गुड बेटा, ग्रेट. और बताओ बेटा, और कोई डाउट्स आ रहे हैं? ओके बेटा, ग्रेट. So this was delta and echo combined correction, and this was a typical question which comes in our exams related to this delta and echo combined correction. So great. Now we have done the coefficients beta. Now I'm taking you to the healing error correction. So let's go beta. I'm changing the presentation now. Let us now understand the healing error present in the magnetic compass. Healing error is the difference in deviation between that when the ship is in the upright condition and that when the ship is heeled or listed on the same course. To give you an example, if the deviation is observed to be 5 degrees east when the ship is upright and the deviation is 7 degrees east when the ship is heeled heading on the same course, the difference between these two, 5 degrees east and 7 degrees east, that is 2 degrees east, this difference has been caused because of the heeling of the ship and is known as the heeling error. Now let us go into the cause of this heeling error. When the ship heels or lists, the compass or the compass card still remains horizontal due to the gimbal arrangement present around the compass. Let us understand it from the diagram. Now in this diagram you can see the ship is in upright condition in this particular diagram. The vessel is upright. This is the compass bowl, and in this particular ship we have a permanent magnetic field present in the vertical orientation. You can see we have a vertical magnetic field exactly below the compass card acting vertically downwards. This particular vessel has the blue end on top closer to the compass and the red end at the bottom. Now a magnetic field acting vertically downwards at the compass location or compass position will cause no deviation when the ship is upright. Now, if you have a look in the diagram, the vessel is upright. You can follow the laser pointer. The compass bowl or compass card is also perfectly horizontal. And in this particular situation, no deviation is generated. Why no deviation is generated? Because the card is horizontal. The magnetic field is acting vertically downwards. Both are perpendicular to each other at 90-degree angle to each other, and being perpendicular, this vertical magnetic field does not cause any deviation at all. Now, as soon as the ship heels to either side, now you can have a look in this particular diagram. The vessel is heeled to the port side. As soon as the vessel is heeled, this particular field now acts on the compass at an oblique angle. Why has this happened? The ship has heeled to the port side. We are looking at the ship from the stern. The ship has heeled to the port side, whereas the compass bowl or the compass card still remains horizontal because of the gimbal arrangement. So this magnetic field now acts at an oblique angle. It is no more at right angles to the compass card. And since it acts at an oblique angle, one of its factors, if you consider this magnetic field as R component, and the vessel has heeled by an angle I is the angle of heel, then its horizontal component, the horizontal component of the magnetic field R, which comes to R sine I, is now acting on the compass card. So as soon as the vessel has heeled, there is a component of the R component, R factor, which is acting in the horizontal plane, that is R sine I, and this is what causes the heeling error. You can see in the next diagram, the vessel is having a starboard heel here. The card remains horizontal, and in this case, the horizontal component of this field, that is R sine I, is acting on the compass card now and is generating the heeling error. Moving ahead now. Now when the vessel is rolling, this oblique field or force acts in opposite direction during the port and starboard rolls, leading to oscillation of the compass card. You can see in this condition the vessel was upright, the vertical field was not causing any deviation. So you can see here no heel, no deviation. There is no deflecting force. When there is a port heel, you see the vessel's hull has heeled to the port side. The compass bowl remains horizontal. The horizontal field of this oblique magnetic field, that is R sine I, now acts to the starboard side of the ship. So you can see deflecting force to the high side, which is the starboard side, and we have a blue pole basically to the starboard side of the compass location, and this blue pole causes easterly deviation. So it is mentioned here also, port heel, the blue pole is carried to the starboard side, generating a easterly deviation. Now when the vessel heels to the starboard side or rolls to the starboard side, this oblique field now acts in this particular direction. You can see R sine I component of the field is acting in this particular direction. So deflecting force is towards the high side, which is the port side. And in case of the starboard heel, you can see here in case of starboard heel, the blue pole is carried to the port of the compass bowl or the compass card, generating a westerly deviation. This blue pole attracts the red end of the compass needle pointing towards north, and it generates a westerly deviation. So when the vessel is rolling to port and starboard, the field acts in opposite direction, leading to oscillations in the compass card. Thus, rolling makes the card swing from one side to the other side, resulting in a very unsteady compass, making the steering difficult. Now, this healing error is composed of two components. Healing error could be generated because of permanent magnetism of the ship. In that case, it is known as permanent healing error. And this permanent healing error is generated due to the force R or component R. In this particular diagram, we see this is the permanent magnetism of the ship, vertical component, R component of the permanent magnetism of the ship, and this is causing the permanent healing error. The permanent healing error varies as cause of the compass course. The second cause which can generate healing error is because of induced magnetism in the ship, and that is called as induced healing error. This induced healing error is predominantly caused due to induced magnetism in two kinds of structures. If we have a vertical soft iron, VSI, above or below the compass, it is also known as a K rod. This VSI exactly above or below the compass generates induced healing error. Just to give you an example, if we have a centerline bulkhead in the accommodation and there are a lot of vertical stiffeners which are welded to that bulkhead, centerline bulkhead, it will have a substantial soft iron component. There will be a induced magnetism and that will generate induced healing error. So this is one structure, VSI above or below the compass. The second structure which can generate induced healing error is the athwartship horizontal soft iron. That is basically the athwartship beams or transverse beams on the ship. So this is also known as a E rod, eco rod. So these athwartship horizontal soft iron also generate healing error. Whenever the vessel heels, one end of the beam is closer to the compass, which is the high side, and one end goes far away from the compass, thus generating the healing error. Any doubts up to here, beta? Great, beta. Very good. Now we have seen that the healing error is caused because of permanent as well as induced magnetism of the ship. And as per our correction principle of like cures like, we should be correcting both these components with their respective correctors. That is, permanent should be corrected with a permanent magnet. Induced should be corrected with a induced magnet or a soft iron corrector. But in case of healing error, it is not possible to use like cure like principle. We are not able to use this principle. Reason for this is, if we use the like cures like principle, for doing so, the permanent magnets and the soft iron corrector will have to be placed very close to each other. They will be vertically above or vertically below the compass. Since the permanent magnet as well as the soft iron corrector is very close, it will lead to a strong interaction with each other. The permanent magnet is going to generate a lot of induction in the soft iron corrector, making the correction unmanageable. So because of this reason, both these effects, permanent healing error as well as induced healing error, are therefore corrected by using permanent magnets placed below the compass card. Correction is achieved by keeping the permanent magnets in a healing error bucket, which has a counterweight and pulley arrangement. Let me show you in the diagram. You can see the diagram of the healing error corrector. We see we have the compass card in this particular location. And this is the binnacle. We have a permanent blue pole. You see ship's blue pole below the compass. In the previous slide example, we saw that there was a blue pole exactly below the compass. So now what we have here is exactly below this compass card, we have a chain and pulley arrangement. You can see we have this pulley here, or you can call it a sprocket wheel, and we have a chain attached to this wheel. On one end of this chain, we have a counterweight just to balance the healing error bucket. We have a counterweight here, and on the other end of the chain, we have the healing error bucket. There are vertical slots in this bucket in which the magnets can be placed. So we place vertical magnets in this bucket. You can see there are these vertical magnets placed in the bucket. The magnets are placed in such a way that the corrector end should be closer to the compass card. In this particular example, we had a blue pole of the ship which was affecting the compass. So we have placed the permanent magnets in such a way that their red pole is closer to the compass card, thus correcting the healing error. So this is the healing error bucket. You can see the vertical magnets placed inside the bucket. If you have a plan view of the bucket, or you look from top, you will see the bucket will look something like this. All these are slots in which the magnets are placed vertically. So plan view of the healing error bucket showing the slots for vertical healing error corrector magnets. Now, why do we have this sprocket wheel or pulley and the chain arrangement? This arrangement basically helps us to vary the magnitude of the healing error correction which is required. The bucket can be raised or lowered as per our requirement. The compass adjuster can place the magnets in the bucket, and then he can raise the bucket or lower the bucket and see what magnitude of correction is required. Then we have a locking arrangement in the sprocket wheel. Once the bucket is properly corrected in the right position, the sprocket wheel or the pulley is locked in location and the healing error is corrected. Now, since in this correction we have not been able to follow the like cure like principle, this error is going to hold good only for the latitude in which it is corrected. And as soon as the latitude of the ship changes, the error is going to reappear. So that's because in whichever latitude you have corrected the healing error, as soon as the ship changes the latitude, the induced healing error is going to change. But our corrector is a permanent magnet, the correction will not change. So either it will be overcorrected or it will be undercorrected, leading to the healing error getting generated as soon as the latitude changes. If a ship has a very strong induced healing error component, if it crosses the equator, goes from one hemisphere to another, when we go from one hemisphere to another, north to south or south to north, the direction of the Earth's magnetic field changes. In southern hemisphere, magnetic field lines come out of the Earth structure. In northern hemisphere, magnetic field lines go into the surface of the Earth. So if a ship has a substantial induced healing error and it crosses the equator, this correction will need to be done again. Because the induced healing error has changed, we will need to redo the healing error correction. Otherwise, it will make the compass card oscillate when the vessel is swinging, and it will be very difficult to steer the ship. Clear up to here, beta? Any doubts?
This correction is in the northern hemisphere.
Ask again, beta.
This correction is in the northern hemisphere.
This can be anywhere, beta. It all depends upon कि जो ये ship का blue pole बन रहा है ये permanent है या induced है. If this is induced, then yes, it is in the northern hemisphere.
Yes, sir.
Okay.
If we will go to southern hemisphere, so this induced thermal magnetism will be red for the ship.
That's
It is
correct,
blue.
beta. If this is induced healing error, then vessel goes to south hemisphere. This pole is going to become a red pole, and in that case, when you place the corrector magnet, you place the blue end on top.
Yes, sir. So what you are saying, when we will go from one hemisphere to another, like from north to south, so we will put it in opposite direction. This character.
Yes, that's correct, beta. That's correct. But you have to ascertain, before you do that, you have to check and confirm that the major part of healing error on your ship is induced healing error. So if it is so, then you take out all these magnets and you turn them by 180 degrees. The red end comes at the bottom, blue end comes at the top, and you put them again in the bucket. So that will ensure that the correction remains appropriate. But if the major component of ship's healing error is permanent healing error, then you don't need to do this. So you will need to first confirm which is the major component and then do this, right?
Sir, how we can confirm that healing error is present, whether it is induced or permanent?
Okay, all right. Now you are going little deeper. अब ये कैसे पता चलेगा बेटा किसी शिप पे कि जो हीलिंग एरर है वो परमानेंट है या इंड्यूस्ड है? सो फॉर दैट बेटा आप ध्यान से उस शिप के जो कंस्ट्रक्शन डॉक्यूमेंट्स है ना उनको चेक करो. सी द लैटिट्यूड वेयर दैट शिप इज बिल्ट. जिस भी यार्ड में जहाज का कंस्ट्रक्शन हुआ है, सो सी व्हाट इज द लैटिट्यूड ऑफ दैट यार्ड. अगर आपका कंस्ट्रक्शन इक्वेटर के पास हुआ है, क्लोज टू द इक्वेटर, ओके, देन परमानेंट हीलिंग एरर विल बी वेरी वेरी लेस, बिकॉज इक्वेटर के पास जो हमारी मैग्नेटिक फील्ड लाइंस होती हैं दे आर ऑलमोस्ट पैरेलल. सो अगर इक्वेटर के पास आपका शिप बना है and the permanent healing error is very very less, obviously induced healing error will be the stronger component. On the other hand, अगर आपका ship higher latitude में बना है, the latitude is high, you know, as you go in higher latitude, the magnetic field vertically down or vertically up, the angle starts to increase. At the equator, lines are parallel. At the poles, the lines are perpendicular, vertically up and down. The dip angle is increasing. So if it is built in higher latitudes, then the ship is going to have substantial permanent healing error. So that gives you a good idea of what to do. Okay, beta?
Okay, sir. But it will not be documented in any other papers, right? In any form?
No.
Okay.
No.
Got it.
It will not be documented anywhere. Only thing, you can see the location where the ship is built and then you can check it from there.
Understood.
Okay, let's go back to the presentation. Now going further into the correction of healing error. As per the theoretical correction method, the ship is made to heal when it is heading north. And when the ship is made to heal, the healing error is generated. The card deviates, indicating the presence of the healing error. And whatever is the healing error, this can then be corrected using the magnets in the healing error bucket. Now practically, this method is going to be very, very time consuming and cumbersome. It is going to take a long time to heal the ship to one side, and we need a substantial heel angle to properly judge the healing error and correct it. So instead of healing the ship, we assess and correct this error with the ship upright. So how can we judge this error in the upright condition? For this, we use a special instrument which is known as a vertical force instrument, in short a VFI. So for assessing the vertical field at the compass location, we use an instrument called the vertical force instrument. Let me show you the diagram. A vertical force instrument or a VFI is very similar to a dip needle. A dip needle is free to move in the vertical plane, and wherever on earth it is placed, as soon as it is released, it is going to align itself in the direction of the magnetic field lines, giving us the dip angle. So this VFI is also very similar to a dip angle. We have a knife edge support, and on this knife edge support, we have a magnetic needle. This magnetic needle is free to move in the vertical plane. So one end, this is the blue end of the magnet, and this is the red end of the magnet. On this knife edge support, it is free to move in the vertical plane. So what the compass adjuster does is, he first takes the VFI, vertical force instrument, and he places it at some place ashore, away from any disturbing magnetic field. So when it is placed in an area where there is no disturbance of any magnetic field, this needle is going to align itself in the direction of the Earth's magnetic field. In the northern hemisphere, the red end will be pointing downwards. In the southern hemisphere, the red end will be pointing upwards. Now there is a slider weight which is provided on this needle. You can see this particular weight here. This weight can be moved in whichever location we require. There is a scale also provided. We can see the scale location of the weight. So what is done is, let us assume that we were in the northern hemisphere, and this red end of the needle has gone vertically downwards. This is pointing downwards in the direction of magnetic field line. The blue end has gone upwards. So this weight is initially placed exactly on top of the support, and as soon as the needle stabilizes with the blue end pointing upwards and red pointing downwards, we slide this weight to the high side. So we slide it towards the blue side. Now you see the force of gravity is going to counteract the force of the magnetic field, and this blue end which was pointing upwards will start to slowly come down. As you take the weight away from the support, the lever at which the weight is acting increases, and it starts to balance the magnetic field. And there is also a spirit level indication which tells us whether the needle is horizontal or not. So as we move the weight, we keep on checking the spirit level indicator, and we take the weight to that location where the needle becomes horizontal. So you see in this particular location, the weight is trying to pull the blue end downwards. Magnetic field is trying to take the blue end upwards. Both are balanced exactly equal to each other, and the needle is horizontal. So in this case, it is known as a balanced vertical force instrument. The VFI has been balanced. Once the VFI is balanced in this particular way, the compass adjuster keeps it carefully in the box, and he now brings this box on the ship, and he places this box or this VFI, vertical force instrument, in the compass location. The compass bowl is lifted up from the binnacle and placed on the side, and this VFI is made in such a way that it can fit exactly in the compass location. So this VFI is placed in the compass location. Now if there is any vertical field in the compass location, the needle will not stay horizontal. If there is any vertical field, the needle will start to point up or down. So if the needle does not stay horizontal, it immediately tells us that there is a vertical field in the compass location. What the compass adjuster now does is, he does not touches the weight and the needle. He places the healing error bucket, and he places the magnets in that bucket. The magnets are placed in such a way that this VFI needle should become horizontal again. So he adjusts the magnets, which side, which red or blue pole has to be put upwards or downwards, and he adjusted the distance of the healing error bucket from the compass location so that this VFI needle becomes horizontal again. When the VFI needle becomes horizontal again, we can check it from the spirit level. As soon as it becomes horizontal, this tells us that at the compass location, the vertical magnetic field has been counteracted by the healing error bucket. So whatever magnetic field was present, vertical magnetic field at the compass location, which was causing the needle to go up and down, has been corrected now using the healing error bucket. So same thing is mentioned here. First, the VFI is placed ashore away from any disturbing magnetic field. It is adjusted or balanced. That means the needle is made horizontal by counteracting the magnetic field with the weight. And then it is brought close to the compass or brought in the compass location. The dipping couple acting on the needle is indicated on the instrument, giving us an assessment of the vertical field, which is corrected using the healing error magnets. Is the procedure clear, beta? Any doubts? Very good, beta. Great. You can now see the healing error corrected magnet in this diagram also. This is the healing error bucket. And this is basically placed in a tube. We have a tube here. The tube ensures that this healing error bucket stays vertically in line below the compass card. When the ship heels, this does not swing around and is held in place by the tube. So in this you have the slots, and in the slots we have the healing error corrector magnets. This is connected with this particular chain. The chain goes up to here, and we have the counterweight on the other side of the chain here. We have a pulley arrangement here on which this chain is wound. Okay, beta, great. That was the healing error and its correction. So I'm closing down the presentation now. Okay. Now, beta, we have seen all the 5 coefficients, alpha, bravo, Charlie, delta, echo, as well as the healing error. We have seen how these coefficients are individually corrected, how healing error is corrected. Now we are going to see the full procedure in detail, step by step. How does a compass adjuster starts this correction procedure when he comes on board? Right from beginning to end. Which corrector is placed first, which is placed at number 2, at number 3, how the sequence goes on, and how the correction is done, the full procedure. So we get a question on the compass correction also. So you may get a full 25 marks question on what is the procedure or steps followed in correction of the compass. So let's see that, beta. So opening up the presentation now. Let's now understand the complete procedure of the compass correction, total compass correction, including all the coefficients. We have already seen all individual coefficients, coefficient A, B, C, D, and E, and we have seen how they are corrected individually. Now we are going to see when a compass adjuster actually corrects the compass on board, what is the sequence he follows in correcting the compass, and what are the steps involved in the correction. The first and foremost important thing to consider for the compass corrector is the order of placing the correctors. We have correctors for correcting different coefficients. The first thing which we need to analyze is what should be the order in which the correctors should be placed. We cannot place them as per our liking and choice. We do not have a choice here. They have to be placed in a specific order only. This order is, first of all, the soft iron correctors are placed in the compass binnacle. And in these soft iron correctors also, we have the flinders bar followed by the spheres. After placing the soft iron corrector, the next correction which is done is the healing error correction. So permanent magnets are placed in the healing error corrector bucket and the healing error is corrected. After the healing error correction, the next correction which we do is placing the horizontal magnets to correct permanent B and permanent C. The larger coefficient out of two, that is between permanent B and permanent C, is corrected first and the weaker coefficient corrected later. This is the sequence what we follow for correction. Moving ahead now. Now, why do we follow this specific sequence? There are certain advantages which we achieve when this sequence is followed. The first thing, why the flinder bar is placed before the spheres. Though the flinder bar is used mainly to correct the induced P coefficient, it also provides a small correction for coefficient delta, coefficient D. When the spheres are placed after the flinder bars, this additional effect is compensated and we ensure that the coefficient D is not over-corrected. Second, why the soft iron correctors are placed before the healing error permanent magnet correctors. The soft iron correctors partially correct the healing error. So once you place the soft iron corrector, the healing error is corrected partially and whatever healing error remains can then be corrected by placing the healing error correctors. In case the soft iron correction is not done before, the healing error correction will be overdone. The healing error will be over-corrected. Now the third concept, why do we place the soft iron correctors before the permanent correctors, that is permanent B and permanent C? The soft iron spheres increase the mean directive force at the compass location, thus allowing for a more accurate correction of permanent B and permanent C later on. As the spheres are placed, the mean directive force at the compass location increases. This increase in the mean directive force result in reduction of the deviation because of any coefficient. So this gives us a more correct or more accurate correction for permanent B and permanent C. The permanent correctors also induced some magnetism in the soft iron correctors, causing a disturbing field at the compass location. When the permanent magnets are placed after the soft iron correctors, the adjuster is able to compensate this disturbing field. Now the permanent magnets also induced some magnetism in the soft iron correctors. Since the cause is the permanent magnet, when it is placed later on, the permanent magnet can be adjusted so that this extra induction does not cause any disturbance in the compass correction. Moving ahead now. Now there are many variations in the methods which we use for compass correction. Some methods are used to correct the compass, a brand new compass where there are no correctors placed for a brand new ship. And some of the methods are used for adjusting the compass later on, a partial adjustment. Now what we see here is the analysis method which is used for a full scale correction of the compass. That means if we have a brand new compass without any correction placed on board, the analysis method can be used to correct that compass and prepare the deviation card. So in this method, deviation is observed on various headings, analyzing the coefficients and then making the corrections in the order of placing correctors as we discussed in the previous slides. Once the correctors are placed, the ship is re-swung to check for any large deviations left, and finally leaving only a small amount of deviations. So with the order of placing characters clear in our mind, let us now go into how each of the character is evaluated and placed. So first of all, we go for the flinder bar. This is the first character to be placed. Now it is very hard to calculate the exact amount of flinder bar that will be necessary or required in a particular ship and compass. We do not have any precise instruments or tools with which it can be exactly find this out. So the experience of the compass adjuster comes very handy to him, and this guides the compass adjuster about the length of the flinder bar. As a general rule, sufficient flinder bar is placed to correct 3 to 4 degree deviation when the ship is heading in a easterly or westerly heading. In case the funnel is very close or it is far away from the compass location, the correction magnitude has to be varied accordingly. When the compass adjuster approaches the ship, he looks at the structure of the ship and he gets an idea what is the location of the funnel with respect to the compass, what is the distance between them, and if he finds it a normal distance, a regular distance, he will do the correction of up to 3 to 4 degree of deviation. However, in case he observes that the funnel is too far away from the compass or the funnel is very close to the compass, he will vary the amount of correction by the flinder bar. The second determining factor could be the size of the funnel. Now this 3 to 4 degree deviation is for a regular funnel of a handy medium size funnel. In case the funnel of a ship is too large or too small, in that case also the correction is adjusted accordingly. Now the next correction after the flinder bar are the soft iron spheres for correction of coefficient D. For placing the spheres, the compass adjuster needs to obtain the deviation on all the cardinal and intercardinal heading. So before he goes ahead with the correction, he swings the ship a complete round and he notes down the deviation on all the cardinal and intercardinal headings at least. Now these deviation readings help him to ascertain or evaluate what is the magnitude of all the coefficients. We have formulas for the coefficients with which we can calculate their magnitude, and this helps us to ascertain what is the amount of correction we require. Like for example, the magnitude of coefficient D can be obtained by using this formula. Coefficient D is equal to deviation on northeast heading minus deviation on southeast heading plus deviation on southwest heading minus deviation on northwest heading divided by 4. So once coefficient D is corrected and the compass adjuster knows what is the magnitude of correction he needs to make, he takes the ship on any one of the intercardinal headings. Why do we go on an intercardinal heading? We are aware that all the coefficients are corrected on the heading where they are the most powerful. Coefficient D, we are aware, is the most powerful on intercardinal headings and it is 0 on cardinal headings. So the ship heads on any of the intercardinal headings. The soft iron spheres are brought close to the compass location. They are placed on the side channels fitted port and starboard of the compass location on the compass binnacle. The spheres are placed initially in the maximum outstretched position, far away from the compass, maximum distance far away from the compass. Once you place the spheres in the channel, you will see a change in the heading shown by the compass. Then slowly the compass adjuster moves the sphere closer to the compass. Now as the spheres come close to the compass, you see the heading change increasing gradually. Now the compass adjuster brings the sphere to the required distance where the change in heading is exactly the same, which is equal to the magnitude of coefficient d. That is the correction what we require. Both the spheres are usually at the same distance from the compass. If the compass is placed on a normal merchant vessel in a centerline location, both the spheres are equidistant from the compass. Once the required correction is achieved, the compass adjuster tightens the bottom nuts of the soft iron spheres so that they remain firmly in place. And after this, he notes the location as per the scale. A scale is put on both side channels, and he notes down the location of the spheres as per the scale, and this is noted down in the deviation card. Clear up to here, beta? Any doubts? Very good, beta. Great. Next is the healing error correction. Healing error is corrected using the vertical force instrument, beta, which I told you just now. We saw how a VFI is first balanced ashore, then brought in the compass location, and then the healing error magnets are placed to correct any imbalances in the VFI needle. Now, after the healing error, next are the corrections, permanent B and permanent C. The bigger coefficient is corrected first. So the compass adjuster first judges the magnitude of the coefficient and then uses the magnitude to correct the coefficient. So how do we obtain the magnitude? Coefficient B magnitude can be obtained by deviation on easterly heading minus deviation on westerly heading divided by 2. Once the adjuster has an idea about the magnitude of the coefficient, he can now place the fore and aft corrector magnets. So the ship is made to head on easterly or westerly direction. Ship is on a easterly or westerly heading. This is where coefficient B is the strongest, and the fore and aft permanent magnets are placed to correct the coefficient permanent B. The magnets are placed 2 in a row side by side, and the number of pairs can be increased or decreased. Also, the distance of the magnets from the compass location can be increased or decreased as there are a number of slots which are provided in the binnacle. So by varying the number of magnets and the distance of the magnets from the compass location, the compass adjuster can vary the correction for permanent B. Then comes the correction of permanent C. So it is done exactly in the same way as coefficient B was corrected using the deviations obtained earlier. First, the magnitude of coefficient C is obtained. The formula for coefficient C magnitude is deviation on northerly heading minus deviation on southerly heading divided by 2. Once the magnitude is obtained, the vessel heads on northerly or southerly heading, and athwartship magnets, permanent magnets, are placed to correct the coefficient C. Now, after placing these correctors, we move to coefficient A, induced C, and coefficient E. Coefficient induced C and E eco are very rare on a normal merchant ship. Hence, any remaining deviation in the compass is considered to be the result of coefficient A. Coefficient A, if any, is applied as an index error. Coefficient A's value can be obtained as the mean of the deviations on at least 4 equidistant headings. If you remember, we had noted down the deviations before starting the compass correction. The deviations are noted. So the compass adjuster now can easily calculate or find out the magnitude of coefficient A by taking mean of deviations on at least 4 equidistant headings. Normally this is done using deviations on 8 headings, that is cardinal and intercardinal, to get a more accurate reading. After all the corrections are done, the vessel is finally swung very slowly and the deviations are now noted on at least 8 equidistant headings. Most of the compass adjuster now do it every 10 degrees and they check that all the coefficients have been reasonably corrected. Then we record a table of deviations remaining uncorrected. Along with the deviations, we note down the latitude and longitude of the place where the correction is done, the date when the correction is done, the time, and also the position of all permanent magnets with their directions. For example, for a fore and aft magnet, the marking which is made on the deviation card is, say for example, red forward or blue to starboard for a athwartship magnet and blue upwards for a healing error corrected magnet. The position of the healing error bucket and the length of the cylinder bar and the scale position of the soft iron spheres are all noted down in the deviation card. Also, the value of variation which is there at that location, present at that location, which was also used to carry out the adjustment, is also noted down in the deviation card, thus completing the correction of the compass and preparation of the deviation card. So beta, any doubts in the compass correction now, anywhere?
Sir, can we put this formula in coefficient A? अगर coefficient A या B, C, D मतलब जो भी आता है, तो उसमें ये formula सर लिख सकते हैं additionally या फिर इसमें से?
Yes, why not? You can write this beta for sure.
Okay, sir.
Okay, beta, great. So I'm closing down the presentation. Okay, all right. So that was compass correction, the sequence, and how do we tackle all these coefficients one by one. So let's take a short break, beta. Let's take a quick 5 minutes break. Then we come back. Now what remains are the typical questions. So let me show you what kind of typical questions can come in the exams. So let's meet after 5 minutes. Okay, beta, आगे वापस चलें आगे.
Yes, sir.
Okay, great. Very good. So now we are going to see some typical questions which come in our exams. We have done the topics, we have done the theory part. Straightforward questions can be answered directly. If they ask you about any of the coefficients or healing error or the compass correction, that can be answered. But sometimes the questions are asked in a little tricky, complicated way. So how to answer that? Another is, in some of the questions you may need to find out the sign of a coefficient, whether it is positive or negative. So how to find the sign of a coefficient, that also I'll tell you. So let's see these questions one by one, beta. So we have the next question on the screen now. The question says, on board a vessel with a constant 2-degree east deviation on all the headings, following permanent corrector magnets were observed, placed as given in the compass binnacle. Number 1, corrector magnet in the fore and aft direction with the blue forward and the red aft. Number 2, a corrector magnet in the athwartship direction with red on starboard and blue on port. Explain with suitable sketches what could be the reason for placement of correctors in the above manner. And part B of the question asks, what could be the reason for a constant deviation on all the headings? Let us now try to go into detail and understand the answer for this particular question. Now we are aware that the fore and aft corrector magnets, they correct permanent B coefficient of the ship. Now if we have a corrector magnet which has a blue end forward and a red end aft, it simply shows that the ship has a red bow and the blue stern. If the ship is having a red bow and we place a corrector magnet with the blue end forward or blue end towards the bow, this corrector blue is going to cancel out the red bow of the ship. Now a red bow and a blue stern happens when the ship is built on any northerly heading. Let me show this to you using a diagram. You can see a particular ship here. Now let us assume that this ship is being built in the yard on a northerly heading. If the ship is built on a northerly heading, we know that there is a red pole in the south part of the earth. Southern pole of the earth having a red polarity. The north pole of the earth has a blue polarity. Magnetic lines of force, they come out from the red pole and they go towards the blue pole. So this is the direction of the magnetic field lines. So if the ship is being built on a northerly heading, the magnetic field lines will be entering from the stern and leaving out from the bow. The part where the lines enter gets a blue polarity. That's why you see the stern of the ship has a blue polarity, and the part where the magnetic lines of force come out gets a red polarity. So that shows us the bow of a ship has a red polarity. So this tells us that the vessel is built heading north. Now moving on to the second part of the question. Athwartship magnets placed in the binnacle, they correct coefficient permanent C. The placement of the corrector magnet shows that the ship has a blue pole on the starboard beam or starboard side and a red pole on the port beam or the port side. You see, the question mentions that the corrector magnet is having its red pole to starboard. This red pole of the corrector magnet to starboard cancels out the blue pole of the ship on the starboard beam. Now, a ship which has a blue pole on the starboard side and a red pole on the port side, this kind of magnetism in the ship happens when the vessel is built on any easterly heading. Let me show you through a diagram. You see this particular ship which is built on a easterly heading. If the ship is built on a easterly heading, the south pole being the red pole, south pole of the earth being the red pole, magnetic lines of force come out of the south pole. They are going to enter through starboard beam. So starboard side of the ship is going to get a blue polarity. The question says that the corrector is having a red end to starboard. So this red end cancels out the blue pole of the ship, thus correcting coefficient permanent C. So the placement of the corrector magnet in this particular orientation, red to starboard and blue to port, immediately tells us that the vessel has been built on any easterly heading. Now when we combine both these two factors, we come to know, combining above, we can infer that the vessel has been built on a northeasterly heading. The heading of the ship is having a northerly component, which results in a red bow and a blue stern, and it is having a easterly component, which results into the blue pole being on the starboard side of the ship and red pole being on the port beam or port side of the ship. So vessel has been built on a northeasterly heading, resulting in the ship's permanent poles being generated as they are stated in the question. Now moving on to the second part of the question, it says, what could be the reason for a constant deviation on all the headings? Now we are aware that a constant deviation on all the headings is generated by coefficient A. Continuous deviation on all the headings is generated due to coefficient A. So same is to be explained in this part of the question. You can make the deviation diagram for coefficient A and explain this diagram. That takes care of the second part. Is that clear, beta? Any doubts? Very good, beta. Great. Let's move on to the next one. Now, while studying the coefficients of the magnetic compass, you will see that all these coefficients are denoted by positive or negative signs. We are now going to understand how this positive and negative sign is given to a coefficient. Now, to find out whether a coefficient is positive or negative, we have to check the deviation generated by that particular coefficient with the vessel heading in a direction between north and northeast. If the deviation generated is east, the coefficient is considered positive, and if the deviation generated is west, the coefficient is considered negative. So to determine the sign of a coefficient, assume the vessel on a heading between north and northeast and check the deviation generated by that particular coefficient. Deviation generated is east, the coefficient is considered positive. Deviation generated is west, the coefficient is considered negative. Let me show you by a diagram. Let us assume that we have a ship which is built on a northerly heading. So if a ship is built on a northerly heading, this red represents the red pole of the earth. The blue square represents the blue pole of the earth. Magnetic lines of force, they come out of the red pole and they go into the blue pole. The arrow shows the sign of the magnetic field lines. Now you can see these magnetic field lines are going to enter from the stern of the ship. And wherever the magnetic field lines enter, you get a blue polarity. So this particular ship has a blue stern. The magnetic lines of force are going to come out of the bow, giving it a red polarity. So this particular ship has a red bow. So a ship which is built on a northerly heading will have a blue stern and a red bow. Now let us try to take this ship on a heading between north and northeast and try to see what kind of deviation these poles generate. So we have placed the ship on a heading between north and northeast. The bow is having a red polarity and the stern is having a blue polarity. Now you can clearly see the red bow is going to repel the red end of our compass needle. Likewise, the blue stern is going to repel the blue end of our compass needle, and it is going to turn the compass in the anti-clockwise direction or the westerly direction. You can see this direction by the yellow arrow. So since a westerly deviation is being generated, this coefficient will be considered as negative. So this is basically permanent B coefficient, permanent B, and this will be minus PB coefficient. So you can summarize, minus PB coefficient is generated on a ship which is built on a northerly heading. Now let's try to analyze this for a ship which is built in southerly heading. You can see a ship which is built on southerly heading. The lines of force are going to enter from the bow now, so giving it a blue polarity. So we have a blue bow, and the lines of force are going to come out from the stern of the ship, giving it a red polarity. So the stern of the ship is red. Now let's take the ship on a heading between north and northeast. We see the ship heading between north and northeast. It has a blue bow and a red stern. Now if you look carefully, the blue bow is going to attract the red end of the compass needle towards itself, so generating a easterly deviation. Likewise, the red stern is going to attract the blue end of the compass needle. Moving, the compass needle is going to turn clockwise, generating a easterly deviation. So this coefficient, which is permanent B, will be considered positive, plus permanent B. So you can summarize, plus PB is generated on a ship which is built on a southerly heading. So the conclusion what we get from here is negative PB or minus PB is generated on a ship built on northerly heading, and plus PB is generated on a ship which is built on a southerly heading. Is that clear, beta? Any doubts coming in? Okay, great. Now once you know this beta, that minus PB is generated on a ship built on northerly heading, you can directly use this relationship in the questions also. I will show you a question now where this is directly used. So let's move ahead. Now let us analyze this positive and negative sign convention for coefficient permanent C also. Let us assume that we have a ship which is built on a easterly heading. A ship which is built on a easterly heading, magnetic lines of force are going to enter from the starboard beam, giving it a blue polarity, and they are going to come out of the port beam, giving it a red polarity. Lines of force come out of the south pole or the red pole of the earth, and they enter into the north pole or the blue pole of the earth. So a ship which is built on a easterly heading is going to have a blue starboard side and a red port side. Now let's take the ship on a heading between north and northeast. You see the ship heading in a direction between north and northeast. We have the compass needle present here. There is a blue pole on the starboard beam, and there is a red pole on the port beam. Now you can clearly see the red pole on the port beam is going to repel the red end of the compass needle. Likewise, the blue pole on the starboard beam is going to repel the blue end of the compass needle, turning it clockwise or generating easterly deviation. You can see the compass needle is going to swing as shown by the blue color arrow, generating easterly deviation. Now since easterly deviation is generated, this will be called as plus PC, plus permanent C. So it can be summarized, plus PC is generated on a ship which is built on a easterly heading. Let us analyze this for a ship which is built on a westerly heading. So this ship is built on a westerly heading. We have the red pole, south pole of the earth represented by this square. We have the blue pole, the north magnetic pole of the earth represented by the blue square. Magnetic lines of force come out of the red pole, enter from the port beam, giving it a blue polarity. Wherever the lines enter, we get a blue polarity. The lines of force come out from the starboard beam, giving it a red polarity. Wherever the lines of force come out, we have a red polarity there. So this particular ship has a red starboard beam and a blue port beam. Let us analyze the ship on a heading between north and northeast now. So we have the same ship here heading somewhere between north and northeast. Starboard beam is red as mentioned in the top diagram, and port beam is blue. Now you can clearly see the blue port beam is going to attract the red end of the compass needle towards it, making the compass needle move anti-clockwise looking from top or generating a westerly deviation. This deviation is shown by the yellow color arrow here. Likewise, the starboard beam having a red polarity is going to attract the blue end of the compass needle, generating a westerly deviation. Now, since a westerly deviation is being generated, this will be considered as negative. So this is negative PC, negative permanent C. So negative permanent C is generated on a ship which is built on a westerly heading. So this is how we can find out the sign of any coefficient using the deviation generated on a heading between north and northeast. Clear, beta? Is that clear up to here?
So this will be only for permanent.
बेटा you are not coming clear. थोड़ा mic से धीरे धीरे बोलो clearly.
So this will be also for induced magnetism.
Yeah, that's correct, beta. For any coefficient, you can test whether it is plus or minus by observing the deviations. Okay, great. Let's move ahead. We now move on to our next question. The question is in 3 parts. Part A of the question says, if a ship has negative PB and a positive PC, in which quadrant was she heading when built? Part B of the question says, if the directive force on northerly heading is greater than the directive force on southerly heading, what coefficient is present and what is its sign? And the third part of the question says, if directive force on easterly heading is greater than directive force on westerly heading, what coefficient is present and what is its sign? So let us try to analyze and understand this question part by part. We go into the first part. If a ship has minus PB, negative PB. Now we just saw that a negative PB is generated on ships which are built on northerly headings. Let me again show you the diagram. You can see we have a ship which is built on a northerly heading. It has a red bow. If you take the ship on a northeasterly heading, this red bow repels the red end of the compass needle, generating a westerly deviation, which gives rise to minus PB. So question says that the vessel has minus PB. So minus PB is generated on a ship which is built on northerly heading. So this simply tells us that the heading of the ship on which it was built has a northerly component. So whatever heading she was built on certainly had a northerly component. Now the question says that the ship has positive PC or plus PC. Positive PC is generated on ships which are built on easterly heading. So let me again explain this to you using the diagram. You have a look at this particular ship which is built on an easterly heading. It has a red port beam and a blue starboard beam. Let us take this ship on a heading between north and northeast. So you see here the vessel is heading between north and northeast. You can see that this red port beam repels the red end of the compass needle, generating a easterly deviation, making it plus PC, plus permanent C. So plus PC is generated on a ship which is built on a easterly heading. Now combining both these factors, it clearly tells us that the vessel is built heading in a northeasterly direction. Whatever is the heading of the ship at the time of shipbuilding, it has to have a northerly component which gives rise to minus PB, and it has to have a easterly component which gives rise to plus PC, thus explaining that the vessel is heading on a northeasterly direction when it is built. Is that part clear, beta?
Sir, this is the case even if the vessel is built in any hemisphere, northern or southern, or just only northern?
Beta, any hemisphere. This applies to both the hemispheres.
Okay, sir.
Okay, great. Let's see the second part now. Now moving on to the second part of the question. Second part says, if directive force on northerly heading is greater than directive force on southerly heading, what coefficient is present and what is its sign? Let's try to analyze this statement. Now, directive force on a northerly heading can increase only if the ship has a blue color bow or blue polarity bow. Now, let us understand this using a diagram. Now, I have a ship here and I have placed the ship on a northerly heading. The question says that the directive force on a northerly heading is greater. Now, for the directive force to be greater, the ship's pole should match with the Earth's pole. Now, we know in the north magnetic pole of the Earth, we have a blue polarity. So, north of the compass needle, we should have a blue ship's pole. So, that is only possible when the ship has a blue bow. It is indicated by the blue pole in the diagram now. And at the same time, south pole of the Earth has a red polarity. So if we have a red pole south of the compass needle, it is going to increase the directive force. So an increase on directive force on northerly heading would happen on a ship if the ship has a blue bow and a red stern. Now if a ship has a blue bow and a red stern, which coefficient does it have? Let us try to take this ship on a northeasterly heading. The same ship is now taken on a northeasterly heading, and you can see this heading, it is somewhere between north and northeast. The blue bow is going to attract the red pole of the compass towards it, generating a easterly deviation, telling us that it is a positive permanent B coefficient. Magnetism in the fore and aft direction generates coefficient Bravo. This is permanent B coefficients because these are permanent poles of the Earth, permanent poles of the ship. So this explains that a vessel whose directive force increases on northerly heading has a positive PB coefficient. So the answer to this part will be positive permanent B coefficient. Clear, beta? Any doubts?
Sir, here we have to show the this pole, south pole and north pole.
You can show, beta. You can show. You can show in the first diagram. You can make Earth's north pole and the south pole. So that also can be shown.
सर एक बार नेट डिस्कनेक्ट हो गया था प्रीवियस स्लाइड करिए सर वो स्क्रीनशॉट करता है
Okay beta, okay, all right. This is the previous one beta. Okay, all right. So we have done part B now. Let's see part C also. Now we move on to the third part of the question. It says if directive force on easterly heading is greater than the directive force on westerly heading, what coefficient is present and what is its sign? Now directive force on a easterly heading can increase if there is a blue pole on the port beam of the ship. Let me explain this to you using a diagram. We have a ship here which is on a easterly heading. And the question says that the directive force on a easterly heading is greater. Now for the directive force to be greater, the ship's pole and the Earth's pole should match. So north of the compass, we have a blue pole of the Earth, The Earth's north pole has a blue polarity. So the ship's pole also has to be blue. North of the compass, the ship's pole has to be blue. So if you have a blue pole on the port beam, it matches with the blue pole of the Earth, increasing the directive force. Likewise, if you have a red pole on the starboard beam, it matches with the red pole, south magnetic pole of the Earth, and increases the directive force. So the fact simply tells us that the ship has a blue port beam and a red starboard beam. Now, magnetism in the athwartship direction generates coefficient C. It is generated by coefficient C. So this ship has coefficient C, and this is permanent magnetism. So this is permanent C. Let us now try to find out whether this is positive or negative. So for this, we take the ship on a heading between north and northeast. You can see the same ship here heading somewhere between north and northeast. It has a red starboard beam and a blue port beam. And you can clearly see the blue port beam is attracting the red end or the north end of the compass needle towards it, generating a westerly deviation. So westerly deviation means it has a negative sign. So this coefficient is negative PC. Negative PC is generated on a ship which is built on a westerly heading. So the answer to this particular question is that the coefficient present on the ship is negative PC. If the directive force on easterly heading is greater than the directive force on westerly heading, the coefficient present is negative PC. Clear, beta? Any doubts? Very good, beta. So let's move ahead. We have done this question. Let's see the next one. We have the next question on the screen now. On board your vessel, you notice that a deviation curve of magnetic compass has an easterly bias. That is, the deviation values are more easterly than westerly, as the vessel is swung around in 360 degrees. Analyze and discuss in detail the causes of such a deviation curve. So let us first of all try to understand what the question wants to convey. Let us assume that on a particular ship we go and we see the deviation curve. A normal deviation curve is going to look like something like this, like a sine curve. At a particular heading, the deviation is nil. Then as the heading changes, the deviation increases, goes to a maximum value. In this example, we have taken 5 degrees east. After that, it starts to reduce and then crosses over to the western side. The maximum westerly deviation occurs here, 5 degrees west, and then it again becomes 0. So over the course of entire 360 degrees, this curve shows how the deviation of the ship changes. Now the question says that on a particular ship it has an easterly bias, that is deviation values are more easterly than westerly. So let me show you what the question means. Now you see a different deviation curve, and this deviation curve, if you notice, it has shifted in the easterly direction by this much value. You see this yellow color arrow. Basically the curve has shifted to the eastern side. The right side is the easterly deviation. So it has shifted to the easterly side by a fixed value. Let us assume that it has shifted by 2 degrees east. So what is the cause of such a deviation curve? Now we can see if you check the deviation at any particular point, it will be the deviation in the previous curve plus a value of 2 degrees east. So it was 0 here, nil, and if you look at it here, it is 2 degrees east. It was maximum value was 5 degrees east, and if you look here, it will go up to 7 degrees east. So you see a constant difference in all the deviation values towards the eastern side. Now, what could be the cause of such a deviation? We know of all the coefficients, there is one coefficient which is constant, does not depend upon the heading of the ship and remain constant over all the headings, and that is coefficient A. So this is the coefficient which is present in this particular ship, coefficient A. It has a value of 2 degrees east, and this coefficient A, if it is present on a ship, is usually not shown in the deviation curve. It is applied as an index error. So you can have a normal curve like this, and the compass adjuster is going to mention that coefficient A here is 2 degrees east. So this 2 degrees east can be applied to the value of deviation at any particular heading, and it will give you the deviation for that particular ship. So we need to explain the coefficient A in this question, making the deviation diagram and explaining the deviation on all cardinal and intercardinal headings. Clear, beta? Is that clear? Any doubts? All right, great. So that completes our magnetic compass. Typical questions are done. So I'm closing down the presentation now. Yeah, all right.
मैग्नेटिक इतना काफी है सर एग्जाम के लिए?
Yeah, that's enough, beta. Ab go through the notes which I have sent you, and after that you can start to go through the questions which have come in past papers. Past papers के questions देखो and try to solve them. जहाँ कहीं भी तुम्हें दिक्कत आती है, you can share those questions to me.
Okay.
Okay, all right. So we will stop it here for today, beta. We are done for today, and we will continue tomorrow's class.
Okay, sir. Thank you, sir.
Okay, beta. See you then tomorrow. Till then, bye-bye.